All right. Good morning, everyone. So today we're going to finish our open source exercise, and then I'm sure we're going to have time to begin our feature engineering exercise, which we'll talk more about it when we get to that point. Okay, so as we talked about last class, and I sent you an email reminder this morning, I asked you to basically already come to class with your DayMat all objects already ran and created and appearing on your environment. This took, at least on my computer, I think it took about 10 minutes less time to run it. And so, this depends on your computer as well. But also it depends on the traffic on that website, right? So I don't think just us here, 23 people pulling data at the same time would really have a major impact on the website, but that traffic overall also impacts how fast you can send data to us. And so I think the first time I ran this last year, it took 3 minutes. Well, this time it took about 10, and my computer is the same. So I think it's also a matter of how much traffic that the API has on their side. But anyways, I am assuming that you all already have this DayMat all object created, which is basically, this is the point that we stopped last time. This is where we're going to resume today from this point on. So what I want to do now, so assuming that you did that, then it means you just pulled weather data for 698 site years in this database. So I want to just explore that a little bit. So the first thing I want to show you here is if you run that object name, it may take just a quick moment for it to actually print it because there's so much inside of this object. So what I want to do instead is just ask for the first few rows using the function head. So let's call head of daymat underscore all, just so we can inspect the first few rows without overwhelming our computers here. So this is basically just the first 6 rows, but remember we have 698 rows in this object. And so we have still that column here, column sites, the latitude, longitude, and our predicted variable of strength, which is what was actually measured in those trials. And then we have this column here that is called weather, right? So this column here, weather, is basically what we created as part of that PMAP. And so that's where all of our weather data is saved under. Remember that when we did this so I'm just going to go back in our code here. When we did that for one site, basically we had all those 2,555 rows for that one site because we had day of year from 1 to 365, and then we had, I believe, 5 or 6 weather variables that were kind of like pivoted longer at that point. And then we basically had to pivot wider instead for that one single site. So now that we have this object DayMat all, imagine that this first row was that one that we did on the previous chunk where it was just one site. But now we have 698 rows where the weather data is basically in each one of those rows under the weather column, right? So again, this is a little bit of a different concept as far as having data sets inside of a data set. But it's something very useful when we're using the map family of functions here in R. All right, so let's say if I just wanted to inspect that first cell, just so we take a look at that, we're gonna call the object name. So daymat underscore all $, weather, which is the name of the column. Do not run at this stage. If you run at this stage, it's gonna print for you 698 times that data set, that cell, right? Which you do not want it. Just to pull that first object, we use the double brackets 1 just to pull that first one. So this is what is inside of that first weather data. So we got that dot site and dot year. If you remember, that was part of our wrangling when we were working up here. So on the main level of the data set, which is the AMAT all, we have a year and a site column. And now inside of each one of those tuples under the weather column, we also have site and year. So I just renamed the one coming from DMAT so they wouldn't conflict with our already present site and year at the main level of the data frame. So we have site, year, and then tile number, latitude, longitude, altitude, and then measurement and value and year and day of the year. So this is the same data set as we pulled that for that one single site on the first chunk or in the beginning of this exercise, right? But now we have 698 times that, which represent each different site and year in our main data frame.
What's the measurement?
Sorry, can you say that again?
What's the measurement column?
So the measurement column, let me go back to when we did this for the just one site, just so it's a little bit more or easier to show. So the AMAT one here is exactly the same data set as that, but it's just when we pull for one site only. So day of year goes from 1 to 365. But then the measurement column is the one that has all of our actual weather data. So for this one site year that we pulled alone, we have 2,555 rows. Why is that? If we have 365 days in a year, that's because we have the first 365 rows here are about day length. So if I come here, you're going to see that transition. So right there. So the first 365 rows are day length, and then it resets for precipitation, then resets for temperature, and resets for all the weather variables that are under this column measurement. So the way that we fixed this, and we talked about this last class, was to do a pivot wider, which we did right here. So we pivoted wider from the column measurement and the column value. So if you do that for one site here, then you end up with 365 rows, because now all of your weather variables are their own column instead of being pivoted longer. Now you pivot wide. Anyone has any questions about that? Because I see some confused faces. So we did this for this single site here, right? The AMAT one object that we just pulled for the first site here in that 698 site years data set. But now, or not now, but we already pulled all that weather data for all the site years and assigned that to the AMAT all. So now we basically have to do the pivot longer again, but for each one of these data frames that we got right here. Okay, so our next step here is going to basically be to do exactly that. As far as going from what the AMAT all is right now to an actual final data frame where we have 365 rows of weather data per site year, but unnested. So when I say unnested, maybe this is still a little bit of a confusing term for you, but every time that we have these nested data frames, by that I mean you have at least one column that has more, that the value is not just a single value or character, is actually a full-blown data set or full-blown object, whatever type that may be. This is a nested column. I want to unnest it, meaning I want to take that and bring into the main level of the data frame. So we have all those weather variables in the main data frame level and not nested in the cell. So that's the first thing we're going to do. I want to bring that into this, or assign this to this object AMAT all unnest. So let's start coding here. We give the assignment symbol. We're going to call AMAT all as our object that is starting off. And if you remember, we used this function, I think, once before. We're going to use the function unnest. And then you need to specify which column you want to unnest. So in our case, the column that we want to unnest is called weather. So we're going to say unnest weather. We can go ahead and run it at this point and print it so you can see what it is. Look at that. Maybe not too many of you have worked with a data frame that has almost 2 million rows. Cool. So what's happened here is, if you see now, if you expand it, we do not have anymore that weather column, because we took that weather column, we took each one of those data sets and kind of brought them into the main level of the data frame. So now we have year, site, lat, long, and strength, which is what we had up until they met all. But then all the columns that were inside of that weather column and so the weather column, each cell was a data frame, right? And that data frame had its own columns. So we brought those out into the main level of the data frame. So now you can see the dot site is here, tile, latitude, longitude, altitude, dot year, day of the year. And then we still have that measurement column and that value column in the main level of the data frame. So at this point, DayMat all unnest is not a nested data frame anymore because we just unnested with the unnest function.
Values or only one?
What do you mean?
I mean, you say, on the weather column, we have different data sets.
Mhm.
So it's open only one data set or all of them?
All of them. Yeah. And then, so the way that it happened, so let me, so Aitan was asking here if it kind of unnested just one of the cells or all of the cells. It did all of the cells. And then you may think, well, but now how do I know that this, because if you look just in this table, which we did look down here, I mean, it still has that dot site information and dot year, but even if it did not have that, so imagine that it did not have dot site or dot year. How would you know that all this weather data is about this year and the site on the main level of the data frame? What happens is when you unnested, so basically this data frame has 365 rows. So when you unnested, just that one, it basically turns into 365 rows in the main data frame. But then all the other columns that were already in the main data frame, which is year, site, lat, long, and strength, just repeats. All of them just repeat 365 times. And then it happens for each one of the cells under weather as well. So you know exactly what weather is related to what site and year at the main level.
This is all 398 site years.
For 698 site
Or
years.
698 site years.
Well, yeah, so they met all is, we're just getting the first handful of rows, but it has 698 site years.
This is opening up all those 698 tables.
Right. Yeah, because all of them share the same column names, right? They have different values, but the column names are the same. So when you unnest, it just creates those new column names and just populates all the way down for all of them. So that's why here on DayMat all unnest, we have almost 2 million rows. That's a lot. Yeah. Okay, so the same way that we had to do a pivot wider on when we were doing just for a single site year, we're going to do the same here for all the 698 site years. So we want our weather data to be, each weather data to be its own column, right? Instead of being pivoted longer as it is the default that DayMat gives us. So if you come here, again, on the chunk that we were working on, give it a pipe. We just did this before for the single site year. We're going to do this for all of them at this point. But we're going to use a function pivot wider. So we want to take all the weather data that right now it's in a long format. We want to change that to a wide format. So we're going to say here names from. So this is the column that currently has what will become the column names once you pivot wider. And that column is called measurement. And then we need to say values from, which is the current column that has the values that will go under each one of the new columns once we pivot wider. So if you run this and you print it, now that has decreased our total number of rows to 300, to about 300,000 rows. So from almost 2 million to about 300. Why is that? Why is this number here? So basically, yes, go ahead. Yeah, go ahead.
I can get to each measurement. And made it column.
It's on column. Yep. Yep.
Okay.
So yeah, that's why it decreased the number of rows, right? From about 2 million to about 300,000. But why exactly this number of rows? Yes. So Micah said the number of site years times the number of days in a year. Is that, I think that's what you said, right? Yeah. Yeah, so exactly. So we have 698 site years times 365 days in a year. That is 254,770, which is the number of rows that they all met Nest has right now. Perfect. All right, so now also you're gonna notice that each one of those weather variables is its own column, right? So we have day length in seconds per day, precip in millimeters per day, solar radiation in watts per meter square, or something else, I think. I don't think this name is fully addressing the units. Snow water equivalent, and then Tmax, which is max temperature, Tmin, minimum temperature, and vapor pressure deficit in pascals. Cool. All right. So the next thing that I want to do here is just to use a clean names, just to help us to standardize all these column names that has like, some of them has like 2 dots, and you know, it's kind of messy right now the way that it was specified. So I just want to use a clean names just to help us with that. I don't remember if we loaded the package janitor in the beginning. If we did not, we could just call janitor : clean names. Just to make sure that we have access to that function. So if you run that and now you print it, we still have our about 254,000 rows, and now our columns have just been cleaned, or the names of the columns have just been cleaned a little bit. All right. Okay, so this is basically, this will be the main data set of predictor variables that we're going to use in this analysis. So remember, we have 698 site years. Our goal is to use the observed cotton fiber strength in each one of those studies and create a model that predicts that using weather data. The weather data that we have, that at this point at least, is daily weather data for all these weather variables for each one of the site years that we just pulled and wrangled from DayMat. Now, every time you pull open source data, I would highly recommend that you export what you just did to file. You don't want to be needing to pull weather from DayMat every single time you need that data, especially if you know that you're going to be using this data for like a lot of different things in the future in this analysis workflow. So with that, let's go ahead and export that. So I want to export this as a CSV. So right now it is a typical is a data frame, right? I want to export as a CSV. So let's use the function write_CSV. The object name that we give here is daymat_all_unest. And then now we specify the path. So I want this to be, we want to get outside of code, go inside of data. I want to call this fields weather data.csv. So now if you export that, if you run that, and then you come here on your files tab, you want to inspect on your data folder, you should be seeing a field weather data file right there. All right, so this pretty much is the end of this exercise as far as coding goes. And just a quick recap of what we did in this exercise. We basically use the year, the longitude, and the latitude information to pull daily weather data from DayMat for 698 site years. Again, DayMat is an open source database for weather data that starts in 1980. So it's really, you know, again, any open source data that is generated some other way. So DayMat basically is generated using remote sensing data, observations of weather from the ground, and also some mechanistic modeling behind it, or physical models, to create this continuous weather data across the US on a daily scale. Every time you could get actual weather data from the site where you are studying, that's going to be the best weather data you can get, the most reliable, the most accurate. However, sometimes you don't have that, or sometimes you are looking into the past, right? So you cannot go back in time and put a weather data there, but you can go back in time in DayMat because they have an archive and pull data from there. But these are some of the trade-offs of using open source data in general, and in this case specifically to the DayMat. And then we wrote a code to automate and iterate this process for all those 698 site years. And again, I know that you all submitted your assignments for iteration. This was the reason why we go through that exercise first is as things start getting more complex and complicated with data. As you can see, we were able to pull all that for 698 times using iteration, right? So you're going to start seeing the value of these data science skills as far as creating iterative workflows, the more complex your data is. And then finally, after doing all that, we then exported this so we can reuse in the upcoming exercise. So in this class, I mean, we could go through a lot of open source databases of different types. My goal here was perhaps to show you one of them that's very, very important if your research is outdoors on fields. And then just give you some resources in case you want to explore other types of APIs for open source data. So I left you here some links that you can explore. So one that I use a lot, and I think that this may even have some data that relates to food science in some ways, but it's really a lot about crop statistics in the US. So there is the United States Department of Ag, National Agricultural Statistical Service, crop statistics. They have a lot of data. It's crazy the amount of data they have. It depends a little bit on the crop. So row crops have more data than, for example, tree crops or some vegetable crops, but they still have a lot of data about crop condition, about planted area, harvested area, yield, all at the county level. So it's really a great resource. And if you want to explore that, which we do in my other class, but we're not going to do that in this class, this is a link for an R API to connect to that database. For soil property, so again, if you're working outdoors, your research is outdoors on open fields, knowing soil information along with weather information can be important to characterize that environment. So here's a few soil-related open source based databases that you can explore. Polaris is a really good one. I think it's mostly in the US if I remember correctly, but it's a really great gridded soil layer information across the whole US. If you want to work at the world level or outside of the US, Soils Grid is a great option as well. Here's also a link for you to explore. And then for those of you working in ag, you may have heard of something called SURGO. So SURGO is the USDA Web Soil Survey, or SURGO itself, the data we can find in Web Soil Survey online, but there is a way that you can access an API directly through R to get data for that. So this is the resource for you to look into it. There is a soil water data open source data layer also coming from the US government. I presented a workshop on how to retrieve this data and process. So I left the link here of my workshop material if you're interested. Drought monitor, this is something that impacts directly ag, but for sure also impacts people. So there is also an open source database for drought monitor in the US. I think they update every week or a couple of weeks. So we always get new data coming in. Very good as well. There are different remote sensing tools that we can pull in R. So if you ever work with satellite remote sensing, you may have heard of a satellite called Planet, or PlanetScope is the satellite name. The company name is Planet. This is one R package you can use to pull planet data as well. And then finally, if you're working on any field, especially if you're working with on-farm studies, knowing the elevation differences within a field can be important. So I'm leaving you here one package in R that you can pull open source elevation data for a field. For those of you doing like outside open field type of research, a lot of times I use this elevation database here to determine how to place my blocks. So, connecting this to previous topics that we went through in this class. So let's say I'm working on a new farm. I've never been to that farm, but I want to at least know how should I properly place my blocks so they are along, or imagine that if you have an elevation gradient in the field, you want your blocks to have a consistent elevation gradient within the block, even though different blocks may be at different elevation positions. Yep.
How often would you say that would be like, if you have a plot or like an experiment that's only like 80 by 100 feet, not that like impactful, because I'm assuming that's too small of a zone to like have that be of any use to us, but like maybe a huge field, like an acre or two, then
Yeah.
maybe like.
So, okay, so Zach's question here is about basically the size of the experiment and how elevation can be useful. Elevation specifically, you're asking?
Yeah, or this data sets.
Yeah, so all of these data sets are gonna have their specific spatial resolution, which is like the pixel size of how that information is created. So for the elevation, if you use this package here, Elevator, I think that the best resolution can get is 3 by 3 meters. But you can get access to 1 by 1 meter products, maybe not through this package, but there is a open source free database for elevation at 1 to 1 meter that could be useful as well. Yeah. So just to give you some idea. So when I'm starting a new project, a new study on a farm that I've never been to, even before I go to that farm, I pull Sergo database and I pull elevation and I look at both of those layers because I want my blocks to have a same soil type and be within the same elevation gradient. So then you can pull remote sensing data from previous years to see how crops were growing in that field. So you kind of develop all these layers that give you intelligence about that field even before you ever set foot to it. So when you go to the field, you already have an idea of what to expect and where you're going to place blocks and plots. So that comes back to, so it's open source, but it comes back to designing studies in open fields and give you some intelligence about how you should place your blocks. So you block appropriately and accordingly to the variability of the field. All right. So this wraps up this exercise and conversations around open source. Anyone has any thoughts or questions? All right, I don't hear anything. So you can go ahead and make sure you save the script. And let's go ahead and do a stage, commit, and push to our GitHub repos. So it just staged. Let me say finished open source exercise, commit, and pull, or sorry, and push. So just a heads up, I know that like I do expect you all to be doing this at least at the end of that exercise. And I may or may not ask Arminder to help me to check your repos at some point and make sure that you are doing that. The goal with that is not to, my goal is that you learn and that you are able to implement these using Git and GitHub on your side. So make sure that when I ask you to create those workflows that way, that you do that way and that you do git push, stage, commit, and push at the end of the exercise. First, because it's going to help you to kind of practice this creating GitHub workflows and doing all locally and then pushing. But also, if you think about it, it's going to basically be a resource for you in the future. So maybe, a couple of years down the road, you want to go back to some of this material. Maybe my links on my class have changed. Maybe you don't have access to that anymore, but you're still going to have access on your own GitHub of all the code that we use in the data. So that becomes your own repository of the data that you worked in class. So it's also, even if you lose your computer or maybe something happens, God forbid, but they never know. At least you're going to have some of this always available to you on your personal GitHub account. All right, so now that we finished this exercise, our next exercise is going to be on feature engineering. And we're going to talk a little bit about it in a second here. So I shared with you this morning a script on GitHub, and I asked you to pull the class GitHub get that script and move that into your code folder of this project. So this is perhaps one of the first times I did not ask you to create a new project. So you did not have to create a new project, just move that script into the code folder of this project.
Excuse me, Professor.
Yes.
So I'm trying to push the workflow, but it's asking for my username and password. I do remember my username, but not my password. Is there a way to work around it?
You may have to go to the actual GitHub page and maybe reset password and change things from there. Maybe that's what you're gonna have to do.
All right.
You can use
Thanks.
the
I'll figure. I'll do that.
yeah. So Madhuparna is saying that you can use the PAT, the personal access token as well. Yeah, I think if perhaps if you can create an issue, like if you cannot figure out on your own, you can create an issue on
Yeah.
GitHub, and then we can, like, different people can try to help you out as well.
All right. Thanks.
Thanks, Mark. All right, so please go ahead and close this script. Still on the same project, don't have to close the project, and go ahead and launch the feature engineering partial script. That's what we're going to be working from this point on. Also because it's the same project, but we're starting a new script with new object names. I want to ask you to go ahead and clean your environment. So if you come here on top, there's that broom symbol right there. If you click on it, you can just say yes, and then that's going to basically clear your environment. So we start on a clean slate here on this exercise.
Dr. Bastos,
Yes.
I have already created the project for this feature engineering. Is there any problem, like if I continue with this one?
So if you created a new project, the point that's going to diverge is right now, if you are in the 09 open data, we're going to import the data set that we just exported, right?
Ah,
Which was the field weather data.csv. We're going to bring that into this exercise. If you create a new project, the only thing that you may have to do is to navigate on the path to where the data lives.
okay,
So
I
that's
see.
going to be the difference on your side.
Yeah.
Yep. Okay, so feature engineering. What does that mean? What is this? So especially in data science applied to machine learning, feature engineering is basically referring to the fact that we are creating new variables from the ones that we currently have. So I guess, what I wrote here in the text is the practice of finding better representations of predictors or features to improve the predictive performance is referred to as feature engineering. So another way of thinking about this is sometimes that the variables you do have at hand, they may not be the best representations of what you're trying to model. And so we do feature engineering by using those primary variables and creating secondary variables from them. So with that, our learning objectives today are going to be to apply feature engineering concepts to the DayMat daily weather data that we just obtained and processed, and then export these feature engineered data sets for future and further use when we're going to start learning or start applying machine learning models to this database. So I left you here. The package we're going to be loading is just the tidyverse, which is going to be just that family of packages that we use in tidyverse. So please go ahead and load that. The next step now is going to be to bring in the data set that we just exported, right? So we come here, we give the assignment symbol. We're going to use read CSV because we exported as a CSV. And now we're going to navigate to that file. So .. to get outside of code. We go inside of data, and then we bring in the field weather data.csv. That's the one that we just exported on the previous script. So Ashbin, this is where you're gonna have to perhaps change your path if you create a new project. But for everyone else, if you stay within 09 open data, this path should work. Right, so we have again our 2,000 or 254,000 rows that we exported before, with daily weather data across different weather variables for each one of our site years. As always, we're gonna do some EDA. I hope you're getting tired of me saying this and that it's sticking in your head that you always need to do some level of EDA to make sure that things are okay. So we see here, I mean, we have a lot of columns, so there's going to be a lot of information. But basically, if we focus especially on the weather variables, so day L stands for day length in seconds per day, precipitation millimeters per day. So this is one of those columns that's really interesting if you think about it, even if you do not work with crops in the field. But I think we can all understand that weather data or precipitation data has a lot of zeros, right? Because each day that you do not get a rainfall, you get a zero on this column, right? So there's a lot of zeros, even the median is zero. But we have, for example, in one of the site years in a given day, we had an event of 230 millimeters, right? So that's the maximum of this data frame. We have solar radiation, which is really important. Crops need solar radiation to do photosynthesis, to grow and provide yield. So this is an important variable related to that. Soil or snow water equivalent is basically in places where you have a significant amount of snowfall. Snow also has some moisture in it. And so this is just the moisture coming from snow. In this database, I don't think there is a lot of snow events because we're mostly in the south region of the US, if you remember that map. But we do have one here that is 151 kilograms per meter square. But most of it is pretty close to zero. Our maximum temperature in Celsius is really interesting because, so if you think about it, in a day, if you have daily or if you have hourly weather data, which most weather stations provide you at least hourly weather data, imagine that, you know, during the night is the coolest, and then as the sun rises, starts warming up, goes up, and then as sun sets, it starts coming down, right? So it goes through these daily cycles of weather. So what Tmax is basically, imagine that, let me make a quick drawing here just to perhaps help you to understand. So imagine you have temperature on the y-axis and hour. So imagine that it starts at 0 and it goes until 23 or 11 p.m. Right? So 0 being midnight. So it's really, you know, low temperature. And then as the sun rises, starts to go, the temperature starts to increase. And then as sunset starts to decrease and goes pretty close to the baseline potentially. So what Tmax is on this day, on this hourly temperature within a day, Tmax is basically this temperature, is whatever was the highest temperature of that day. This is what Tmax is. And Tmin is basically whichever hour happened to be the lowest temperature. Let's say it was, normally is right before sunset. So maybe your Tmin is coming from this value. And then Tmax is the highest of that day. That's what Tmax and Tmin mean in our data set. So we see here that Tmax, there was a Tmax of, the minimum was -14. So imagine that within a day, in a given site year, the highest temperature was -14 Celsius. And then the maximum Tmax in a given site year, in a given day, was 49 Celsius, which is pretty hot. On the Tmin side, we had ranging from -28, so the coldest temperature across this data set was -28 Celsius, and the maximum t-mean, which I know can be confusing, but imagine you take the t-mean of all these days and sites and years, and then you look into the distribution of that. So the maximum t-mean was 31. And then vapor pressure deficit is basically just a variable that helps us understand the evaporative demand of the atmosphere, which relates to dryness. So the higher is the vapor pressure deficit, the drier are the conditions that the crop is going through. So this is just a measure of how dry the soil and the atmosphere are for crops. All right, so we checked this quick EDA through just looking at these, at the summary. Now, I always like to do density plots, as you probably have already noticed, because it helps us understand a little bit more this, the distribution of the data and the shape, right? Because just looking at the statistical summaries as numbers, for me is useful. So a couple of ways that I use this, and perhaps I have not explicitly said that, but looking at the minimum and maximum values makes sense and checking if they make biological sense, if maybe there were no typos, you know, if you would have, like some of these variables here cannot be negative. For example, you cannot have negative precipitation, right? So if your minimum precipitation is a negative number, that something is going on, right? Either it was like a typing error, or maybe some of these open source databases, they have ways of coding NAs. Some of them would code NAs as -9999. So if you come on one of these data sets and the minimum is -9999 something, that's probably the way that this database codes NAs, which means that you as a researcher have to know that so you can address it. You're not going to try to model precipitation on -999. It makes no sense, and the model is never going to learn that because that's not true. So you have to be aware of that and then go and say, all these -99 values here, I'm going to change them to actually be NAs in our data frame. We don't have that happening here, but I'm just giving you an example so you're aware. Other ways that I check these data frames, and you can check this later in more detail on your site if you want, is if you have data that is normally distributed, so it's not skewed to any one of the sites, it's normally distributed, the mean and the median will be pretty similar. Let me make a quick drawing of that as well to help you understand this. So let's say we're doing a density plot of whatever variable, like it doesn't really matter which it is. Just let's call that variable X. And then here on the Y, we have the density of that. Imagine we're doing a density plot of this X variable. If you have a normally distributed data frame that a density will look like a normal distribution, your mean and your median are going to be pretty close to each other for a normal distributed data frame. However, if you have a skew distribution, either to the right or to the left, let me show you maybe one that is skewed this way. So another data set or another distribution here in green. This is not normally distributed. We can really see it, right? It is skewed to one side. In this case here, the median is still probably very near to that peak that you're seeing. However, the mean is going to be more towards that tail. So maybe the mean is going to be around here. The reason for that is that the mean is sensitive to outliers. An outlier would be a point that's really far from the center of that distribution. So the reason why this green distribution has a long tail is because you have some observations out here, which are outliers. The mean is sensitive to outliers. The median is not. So the median will always be close to that peak of the density. The mean is only on the peak of the density if you do not have outliers, which if you have a normal distributed variable, mean and median are pretty close because you don't have outliers. If you have a skew distribution that's non-normal, your median is going to be at the peak, but your mean is going to be shifted towards that tail because it is sensitive to outliers. So this is another way that I use the summary function as well to check for things. So if you come here and you see that mean and median are kind of close, then it's probably normally distributed in shape. But if they are really far from each other, then probably it's not normally distributed. So that is how I get that information from the summary. But then we're going to use, again, density plots to look into that. So I'm going to rely on your help here. So I want to plot all the weather variables using ggplot to do a density plot for each of them. I'm going to give you the beginning object, which is the one that we just created, right? So field weather, that's what I want to use here. So field weather, I'm going to give a pipe and I'm going to stop here. So again, my goal is to create a ggplot showing the density of each individual weather variable. Can somebody help me out here? Sorry, Charles, did you say something? No, okay. Okay, so Priscilla said start with ggplot. I like it. At some point, we're gonna have to have ggplot in there, right? So, okay, so ggplot. Well, so we started with field weather and piping that into ggplot, so we don't have to say data equals because that is implicit. But what would you say here now?
Trying to see why would be X,
I like the way you're thinking.
but
We can select the columns first, the ones that we want to plot, and then do the ggplot or not.
So was that Ali?
Oh, Selvin.
Oh, Selvin. Okay. Thanks, Selvin. Yeah. So we could select the columns if we wanted. It could be a step just to. So if we use the select function for that, it could be a step just to make things a little bit cleaner, but it's not the function that's going to make a difference. So I'm going to skip that. We could do it. So I do want to acknowledge that, but I do want to skip that and maybe help you all to think in a slightly different direction. Okay, so Tara is saying, should we do pivot longer for the columns that we want to plot? Yes. Can you share with us why do you think that's necessary?
Because you only move the value and then to plug the density. So if they are like wider, so it's harder to.
Right. Because right now, so we need to have one column to say this column goes on X, right? And right now we don't have that single column. We have, I don't know, 5, 6 weather variable columns that we cannot say X equals to all these columns, right? So yes, that's the way that, and I think Priscilla was also thinking about in that direction. So yeah, that's what I'm trying to help you figure out on your own when you don't have me in front of you to tell you what to do. But that's exactly right. So we want to do, before we get into ggplot, we want to do a pivot longer, in this case, where we basically want to pivot longer all the weather variables. So if I just print field weather just to check again. So I basically want to start on day length. So pivot longer, here we're going to say cols to say which columns we want to pivot longer. So starting on day length, give it a colon. Because those weather variables are all consecutive here on this data frame, we can just give the first and the last one. So we're starting on day length and ending on VP. Before I add a pipe here, I just want to run this so you see what happens. So field weather has 254,000 rows. If we pivot longer, we
It's.
do that.
I think we made a typo.
Oh, yes. Thanks, everyone. Yeah, so I did make a typo. I wanted VP here. Let me do that. We should go back to our almost 2 million rows, right? Which was that original way that Daymat gave to us. But now we do have a column that is called value and now one that is called name. But yeah, this is a step that we would need to do here to get into ggplots. All right, so now if you give a pipe and we get into ggplots, again, our goal is to make a density plot for each one of these weather variables. What else do we need here? Yes, Ruben.
You can arrange by name.
Okay, we can arrange by name. That it's not, so it would help us, perhaps us to visualize the data frame, but it's not what is gonna make a difference to show. So we could do it, I want to acknowledge that. But I'm just gonna skip that just to show you that you don't have to, at least not to get to where we want.
That's the case, in the GQ plot, we can go and as x equal 5.
Yes. So Ruben said on ggplot, we give as x equals to value. Perfect. That's exactly it. All right. Now, can somebody else now help me with the next step?
Geom density.
Geom density, right? So Charishma said here, maybe Shakir online. So geom density is what we need. If we just run this, we're gonna get this, which is really not useful, not what we want. So we're missing a step here.
We want a facet graph by the name.
Yeah, so I think a few of you said that, right? So we want facet. Let's use facet wrap. And which column do we facet by? So if we print here, which is the incoming data frame, which column do we facet by?
I think
Name.
name.
Name, right? So let's use dot tilde name. And I do want to say scales equals free already, because then each variable can have its own X and Y scale instead of everything being the same. So if you run that, then this is what we get for our 7 weather variables. So again, this is daily weather data for each one of these variables across 658 site years. So there's a lot of data going to each one of those density plots. So a few things here to notice. Day length, kind of interesting that you see 2 peaks here. It may be related to like summer and winter where day length changes, right? So that's probably why we have these 2 peaks, and then in the middle you have some values as well as the seasons transition. Precip and snow water equivalent are highly skewed. And again, this is because on a daily scale, you have a lot of zeros, right? You have a lot of days that there's no rain, which is then coded as 0. But then you have long tails because some of these events were high in precipitation and snow water equivalent, but you still have a lot of zeros. So you would expect to see this type of behavior. With solar radiation, Tmax and Tmin, they kind of follow a similar, well, perhaps Tmin not quite as much, but solar radiation and maximum temperature follow a similar shape at least, which I guess it makes sense. For Tmin, it has this interesting peak here towards the end. I really don't know why. It's got to be related to the interaction of seasons and location, right? So we have some places here that may have a different temperature minimum than others just because of the geographical location. And then vapor pressure, we see that there is a peak here towards lower levels, but then also this longer tail here. All right, so I hope that you are realizing that, the summary that we get here from the summary function is helpful, perhaps identify some erroneous errors to give you some intelligence around, what are these values, how much variability you have in them. But then really to understand the shape of that distribution, geom density is your friend here, right? This is what we would need to really understand how are these variables, how are they distributed? I guess any questions at this point before we move on? Yeah.
My computer is restarting, so I can just take a picture.
Oh, yeah, sure. Yeah. All right, so I have here on this next chunk, we're really not coding. I just wanted to print field weather again, just so we can look into these variables. So remember that field weather, it's still 254,000 rows. We only have that almost 2 million rows after we pivot longer, but we just did that for plotting. We're not keeping that format, just so you realize it. So now on field weather, as we already know, we have all these weather variables across 365 days of the year for each site year, right? So our time interval is basically daily. That's how we got data from the EMAT. I want you to think about this for a second, because so it's really good to have high resolution data. In this case, resolution related to the temporal resolution, how much data you get over time, in this case, a daily scale. So it's great to have that type of data. However, plants normally do not respond to one event in a day unless that is an extreme event, right? So unless you have a tornado coming through, or really strong flooding, or something that really impacts significantly and abruptly your crop in a day, normally crops respond to the cumulative effects of these weather over time, right? So if it doesn't rain today, and it has rained maybe a couple days ago, if it doesn't rain today, my crop is not going to die, right? It may die if it doesn't rain in 2 months, but it rarely responds to daily weather data. And this is where feature engineering comes into play. Because if my crop is not responding so much to daily weather, but more to the cumulative effect of weather over time, maybe training models with daily data is not the best approach, because it's going to be harder to make those relationships with a crop response, in this case, cotton fiber strength. So rather than, so plants, they do not respond to that daily scale, they respond to a longer time scale. And so my question to you is, how could we use this understanding that in this specific case, we know we have data, our predictor variables are in a daily scale, but plants, for the most part, do not respond to daily scale weather. How could you use this knowledge to create new variables or new features from the data set that we have right now? That's my question to you, and it's also a question that you're going to answer on the quiz. So let me go there and make this quiz available to you all. Just a sec here. I'll let you know once I make it visible. Okay, so I just made quiz 7 feature engineering visible. It is just a question. If somebody can confirm that you can see it.
Yeah.
Okay, thank you. And I'm gonna give you last time, 4 minutes today to give me an answer there. And again, there is no right or wrong answer. It's just for me to kind of have an idea of how you're thinking around this topic. Right, 4 minutes on the clock. All right, we're getting to the last 30 seconds here. Make sure you submit your answer. All right, we reached the end of this quiz, so make sure you submit it. Again, there's no right or wrong answer in this specific quiz. It's more just for me to see how you're thinking. I was checking some of the answers here, and what I saw was, I mean, some really great comments from you all, and I just want to stress some of the points that I read here. So basically, what we're going to do, the way we're going to address this is by summarizing this daily weather data to a given time window. Okay. So in this case here, there are two components that we're going to have to consider when we're doing that. In this specific case here, feature engineering out of weather data. So one of them is going to be the size of this time window. Why is that? So we have daily data. We're going to make it coarser in time. So we could do it maybe every week, maybe every month, maybe every 2 months, maybe the entire growing season. If we know planting date, harvest date, or approximately when those happen, we could do for the entire growing season. So know, for example, how much rain that crop received for the whole growing season would be an example. What was the maximum temperature over the entire growing season for each one of these side years? If you have more specific data around when it was planted and when it was harvested, which I don't think we have in this data frame, you could also estimate crop stages. So if you do not work with crops directly, this may not be super clear. So I want to explain what I mean by that. So most crops, they grow and develop based on temperature and or light. So that is basically what determines how much a crop is growing, or two of the main things that determine from the weather side how much a crop is growing. So one of the comments I saw here was that we could calculate growing degree days from this database. That is a really good idea. I don't remember exactly if we're going to do that, but that could be another variable that we get from here. Could be growing degree days, that we create that variable based on the temperature data. And then the literature has a lot of different thresholds that relate growing degree days and crop stages. So you could say perhaps, well, growing degree day starts on the day that you plant the crop, that's 0, and then it increases based on how hot or cool a day is and how the crop responds to that and grows in relation to that. So maybe we would know that crops would emerge within maybe 60 growing degree days, accumulation of 60 degree days. Maybe they would go from a plantling to a seedling to maybe one of the vegetative growth stages within another threshold of growing degree days, and so on. So we add these thresholds of growing degree days over the growing season to establish crop growth stages. Why would we do that? So most crops, there are periods of the growth of a crop where they are more sensitive to stress. So if you know that a crop is going to be very sensitive in the sense of if you have a drought, so lack of rainfall around flowering, for example, that is a key stage that if you have a drought during flowering, you're likely going to have an impact on yield because the crop is not going to be able to come back from that stress. However, if you have a drought stress early in the season where the crop does not require a lot of water, it may not matter. It may overcome that stress if you do have water later on. So there's some key crop stages that crops are more or less sensitive to weather stress. And so if you create a time window being crop growth stages, which go back to growing degree days, which go back to temperature, that could also be a window size that we could use. And maybe there are others that I'm not saying here, that I'm not specifying. So maybe you would have your multiple crop growth stages, but then you combine them in different ways and create different window sizes as well. So I think a lot of you, at least of the ones I was able to see, mentioned something along these lines of creating a window size of time that you would then get a summary of weather data within that window, right? But then just determine the window size is not enough, because now it matters what is the summarizing function that you're going to apply to that window. So for example, perhaps the one that we all think of first is to get the mean of something. So I want to get the mean of the temperature within, let's say in a given month. Let's say from April 1st to April 31st or 30th. Within that month, you have all the daily Tmax, right? So let me make a quick drawing here just to illustrate that as well. So let's say that you have a given variable on the y-axis. So let's say that this is Tmax, which we do have on a daily scale. Okay, just imagine that's Tmax. And then you have day of the month going from 1 to 30. 1 to 30. Right, so we have this data right now, right? We have this for all months, not just one, but I'm thinking just 1 month here. So let's say that the Tmax for, it's gonna vary within that month. And this is one side year only. It's gonna vary, right? So we're gonna have, I hope you get the idea here. I'm not gonna do everything, but you have this data varying for each day. What was the Tmax on a given day? So if you determine the window to be monthly, then this is 1 month. Let's say it's April. You want to get just one value from this daily data distribution. You could get the mean. So the mean would be maybe a line that goes through all of these points, right? Like this would be the value of the mean for this month, for this site, and this year. However, sometimes the mean is not the best one, depending on the variable and depending on how crops respond. So for example, perhaps instead of getting the mean Tmax, you want to get the minimum Tmax of this month, which maybe it was this value here. So this value here was the minimum Tmax in this month. Perhaps you want the maximum Tmax, which maybe is this point. Right? So you can extract different things from the data within that window that you created. Now for temperature, it makes sense to get mean, minimum, or maximum, or maybe median. However, does it make sense for precipitation? Does not make sense, right? So imagine that, let me see if I can get a new page here. I don't know how to do that. Okay, maybe this would help. So imagine that you have the same thing, but precip instead of temperature. So you have a lot of zeros. And then maybe you have one day that rained, but a lot of zeros. And then one day that rained a little bit less, right? So if you get the mean here, you're gonna be getting like a value that's really close to 0 because you have a lot of zeros. What would be the better way of getting precip data or summarizing precip data within a given time window? Maybe the median. Okay, I think we could do that. You know what?
Total
Oh, sorry.
precipitation.
Go ahead, Comfort.
The sum.
The
The
sum.
total precipitation.
Absolutely, I totally agree with that. So with the sum, imagine that instead of getting the median, you're gonna see, okay, let's say this was 30 mil, or let's say this was an inch, this was half an inch. and then a lot of zeros. You basically have 1 plus half, 1.5 inch over this time period, because then that's really what the crop saw. The crop really saw 1.5 inch. So getting the mean or the median is not going to fully represent what the crop was subjected to when it comes down to precipitation. All right, so in the next section here, we are gonna basically determine our size window of monthly, and then our summarizing function is gonna be either mean or the sum. So I have another quiz. I was really inspired this time. But this one, I'm giving you 1 minute only to complete because it's a really simple quiz. And then after that, we can catch a break because you're probably needing a break at this point. But I just made available the quiz number 8, summarizing function and weather variables. If you can confirm that you can see it. Awesome. So here's what I'm going to do. I'm going to give you all 5 minutes for break, assuming you may only need 1 minute for this quiz. And so do this quiz, respond, and then take the rest of your time as a break. All right, time is up, so please, for those online, turn your cameras on again, and let's continue here. So our goal now is to, or what the workflow I want to show you is how we would summarize this weather data on a monthly scale. And within that window size, we're going to either get the mean of variables or the sum of them, depending on the variable. Yes, Comfort.
Dr. Bastos, I wanted to ask if the feature engineering stuff is just about summarizing the data, or
So really, like the concept of feature engineering is whenever you create new variables from the current ones that you have, being that the new variables may be a better representation of how your predicted variable respond to that, right? So in this case here, we're summarizing, but it doesn't have to be summarizing. So for example, if you were to create growing degree days from the temperature data, that would also be feature engineering, even if you may want to then summarize growing degree days to some extent. But the fact that you're creating growing degree days from your primary variables of temperature is already feature engineering in itself.
okay. So just like, for example, the way we calculated some vegetation indices from the reflectance values.
Yeah, so
right?
that's a great example, right? So on remote sensing, we get, most of the time, we get information on specific bands, right? So
Okay.
by creating a vegetation index, that could be considered feature engineering as well.
Okay, thank you.
All right, so I want to, so we have not talked or used a lot of dates in R yet, but I think that's a really important topic, especially if you're working with data that is spanned over time, whatever scale we may be. So I want to first introduce you to some date formats. I know these are the date formats that R uses, but I would imagine it's pretty similar across different programming languages. So I'm just going to open that address that I left you there. It's from this website called R Bloggers. And really what I want to show you here is the table towards the lower part of this post. So this is how you would specify, so the percent and then a letter is how you would specify specific date formats that you may want to use. So let's say that let's say that you have a column that has a full date, like it has year, month, and day. And you want to extract something from that. So maybe you want to extract just the day, maybe you want to extract just the year, maybe just the month, maybe something else. I want to extract perhaps the day of year, which is a variable that goes from 1 to 365. There's so many different ways you can showcase dates that what I want to show you here is how you would refer to that. So let's say that you have a date, 2025-03-20, today's date. And I want to know what was the abbreviated weekday of that date. You would use a function where the function is going to ask, what's the format that you want out of this? You would say percent lowercase a. That's going to give you that today was Thursday, right? Or perhaps you wanted the full name. You would say the full weekday name. You would say percent uppercase a. You know, so all of these different formats that you're trying to extract from a from a date data, you need to specify what is the format that you want to get out of it, so you can get out of it whatever you wish. I'm not going to go through all of these, but you can take a look. I left the link here in the script, so you can look later if you wish. But if you think of right now, our data set, so our field weather data set, really what we have here is we have the year, right? So we have a column for year and we have a column for day of the year, which is from 1 to 365. We do not have a month column here. If we want to summarize by whatever window size, in our case, I'm going to show you how to summarize by month. We have to have a column that has month information, which we do not have at this point. So I want to show you how we would do that in R, how we would create that column. So the first part of it is I wanted to show you the format of these different date formats in R because we're going to be using at some point one of these formats to extract the month from a given date. So that's why I wanted to show you this. Also, if you're working with, again, dates or even times in R, I really recommend you take a look at this package called LibreDate. I left you the vignette, the link for the vignette of this package so you can take a look. I'm going to open that here very quickly just to show you what it is. But this package called LibreDate has a lot of really useful functions to transform a string into a date format, because you have to have an object that is seen as a date format in R for you to be able to extract all sorts of things related to date from it. So it has a cheat sheet here that you can go through, but then it really has a lot of really useful functions that can help you extract information from dates in R. I'm not going to go through all of them, but if you work with dates and you need that information to be explicit or even times, take a look at this vignette. I'm sure you're going to find some useful examples here. Okay, so again, our goal is to summarize by month. So we have to have a column that has month information, which we do not have at this point. So we have to fix that. We have to wrangle around that. So that's what we're going to do next in this chunk right here. I left you part of it already, which is basically just starting with field weather, which is our data set that we're using up until this point. And I'm just selecting some variables and also renaming some of them just to make it, to have a better standard way than clean names gave us. So for example, I normally like to have so the name of the variable underscore and then the unit. But in this case here, the units are also separated by underscore. So I don't fully like that. I prefer to just have the units together in one piece, because if you ever for some reason need to extract the unit from these names, you can just do a separate and say that your separator is dot, and then it's going to separate name from unit if you ever need it. We're not going to do that in this exercise, but that's why I like to have a standardized way of naming columns. So I'm just doing some renaming on the go, as you can see, and through a select. So if you go ahead and run this, the FE month, and you print it, is basically the same data frame, just with maybe a few fewer columns because we left some of them behind, and some renamed columns, but it's still 254,000 rows, and in this case, 12 columns. All right, so for us to be able to extract the month from date, R has to interpret that column as a date object, which is a specific type of object. It's just like calling an object a data frame or a list or a matrix. A date is a specific class of objects in R. So we first have to create that, and then from that extract the month. So here on this next, if you just add a pipe here and go after that comment of creating a date class variable, that's what we're going to do first. So it's going to be interesting because the way that what we have right now in this data frame is we have year and we have day of year. So we have like 1980, and then we have like a number going from 1 to 365, right? So right now none of our columns have an actual full date of like 2025-03-20, for example. So the first thing that we're going to have to do here is combine that year and day of year in one thing first, and then tell R that this is a specific format of date, and then extract the month from it. So let's come here on this part of the chunk. You can start coding with me. I want to call this column date underscore CHR, meaning that it's going to be date in a character format first. So what we're going to do here is basically combine the year and date of year together in one column. we're gonna use here the function paste zero. We've used this before. Where I basically want to say year is the first thing I'm joining here. And then I want to put a slash in between. So you put a quote in quotation marks, put a slash, give it another comma, and then let's bring Y day, which is the column that has day of year for us. If you run until this point and you print FE month, now we have this column here that has exactly what we asked it to do. So the year / and then the day of year. And remember, day of year go from 1 to 365. Also notice that this column here is interpreted by R as character. So R is not seeing this column as a date column object yet. We have to change that in the next step. So to do that, come back to the code, give it a pipe. We're going to call another mutate. And now I want to call this new column as date. And here's what we're going to do. We're going to call or use a function called s.date with the D uppercase, as dates like that. We first say what is the column that we want to transform into as date. The column name that we want to transform is date underscore CHR, the one that we just created. And then the next argument here is the format that column is in. It's not the format you want it to be. It's not like I want to say month at this point. This point I need to say the format of this column is this. So if we look into the format right now, it has the full year, a / and the day of year, right? This is the format that's currently in, is that. If we go back to, let's see if I still have that open. No, I closed that. Let me reopen here just to show you. If we go back to look into this, the date formats in R, and go to that table towards the lower part of this post. So what we have is year. Let me see where we can find it. It's probably, yeah. So uppercase Y is the format that we have now, right? So notice there is a lowercase y, which is just the last 2 digits of the year. So we have the full year, right? So 1980 something. So that format is % uppercase y. So we have that, and we have the day of the year, which is, if you look for here, day of year from 1 to 366 is a % lowercase j. That's the format that we have. So what we're going to do is go back to R, go back to where we were writing the as dates, and here we're going to give in quotation marks % uppercase y, which is the format for a full year. We're going to give the / because that's how our strings are. They have a /. If instead of / here, we had used a dash, you would simply come here and give a dash instead. Is whatever the format that you're given is under. And then % lowercase j for day of year. This is the format that our strings are in. So now, if you run this, make sure you put the % in front of the y, you put the / and the % in front of the j as well. And now you print FE month. You browse all the way to the right. Now you have a column called date. Notice that, so the name of the column is dates, but also the class of this column is dates, as you can see right under it. And notice that it understood that you gave a year and a day of year, and already gave you the full year, month, and day format for you. So again, on the as date, we did tell it what was the format that we had, not what we wanted to be. So we had year / day of year. And once you explain what you have, it gives you this format of year, month, day. Anyone has any questions about this? So if you were to just scroll down all the way through this data set, you're going to see that that's the format that you have exactly. So as the year is going to change, you know, after 365 rows, year is going to change, or maybe site's going to change, right? So it's following that format. Again, also notice that the date column is an object type or is a column of type date. And this is the key point, because now that it is a type date, you can extract all sorts of date related things from this full date. I can extract just the year, just the day, just the month, the weekday name, and anything you want out of this. So that's why we wanted to have this in a date format first. Any questions? Okay, so now that if no questions, let's keep going. Now that we have this in a date format, again, we can extract all sorts of things. So let's add a pipe and let's extract the month. So we're going to use a mutate. I want to call this new column as month. And from the LibreDate package, there is a function called month. So we want the month of, and then the object that has the date that we want to use, which is date, right? So we have a column called date, and that column is of a type date, which is the key thing here. So if you run this now, and you print FE month, you're going to see that you have now a column that says month. And it is the numerical value of that month. So 1 is January, 2 is February, and so on. And if you scroll down here, you're going to notice that once it changes from January to February, the month changes to 2, right? So now we have this column month has the values that go from 1 to 12, right? For each one of the months in a numerical way. Notice that is a double type, so it's numerical. Now, let's say I also wanted to have a column with the abbreviated name of the month, so I could perhaps show that in a plot instead. Let's add a pipe, call for another mutate. I want to call this new column month_ABB for abbreviation. So again, I'm telling you the function we're using, but if you are interested, if you want to learn more about this, look at the vignette of the LibreDate package and the cheat sheet of that package. You're going to have all the functions available to work with dates. I'm just showing you the ones that we're using for this exercise. So if I want the abbreviated month, we still use the function month on the column date, but then we change one argument here, which is label. It's called label equals true. If you say label equals to true, and you print FE month, that is going to give us the abbreviated month name instead of the number. And notice how I kept both. I did not overwrite. I kept month as numerical, and I kept month as the string of the abbreviated month name. Yes.
After, for some reason, it wasn't throwing an error at first, but now mine says as for the as.date function, that data underscore character is not found. Any idea?
Check if you have this pipe right here. You do? And what about this one? You had as data?
Yeah.
Yeah. No worries. Easy fixes. All right. Any other question before we move on? Okay. So here's so now we have a column for month, right? So now we can say summarize, including this column on our group by. We can use that information, which is what we're going to do next. So in the next chunk, we're basically going to get the summary of the variables over month, or for each side year and each month, we're gonna get a summary of weather variables, whether it's gonna be the mean or the cumulative value for that. So we're gonna come here on this next chunk. I left you the name that we're gonna use, so give the assignment symbol. We're gonna start with FE month, which is this object above that we just created all those date columns. Give it a pipe. So we're gonna do some group by. That's what we're gonna have to do here. And I will tell you exactly what to group by, and you're gonna see why in a second. So, well, I guess let me tell you this. What we will, or one of the ways to think of our outcome out of this chunk is gonna be, you're gonna have each row is again going to be a side year. And then each summarized weather variable was gonna be a column. So let's say I'm gonna have for a site year, so 1980 Altus, Oklahoma, which is our first site year. I'm gonna have one row for that site and then columns for, let's say, Tmax mean in January, Tmax mean in February, Tmax mean in March, and so on. So all 12 columns for Tmax, one for each month, and then all 12 for precip, and all 12 for fluoridation, and so on. So that's what I want to have, and then where each row is going to be one side year. Right now, each side year is 365 rows. I want to summarize that, and then per month, but instead of having month as a column, we're going to have month as part of the name and be in the column names themselves. So given of at least what you know at this point, what do you think we should include in this group by? Year, I agree. Site, let me put first site, or oh, year, okay, year site, that works. Month, right? So I'm gonna do month, the abbreviated, in this case. So if you, maybe, I don't know if you had a chance to run into this, but when you do a group by and you summarize, which is what we're gonna do, any columns that you do not specify in group by, they're gone after you summarize, right? So I want to add here strength as well, not because strength is an actual group, but just because if we don't specify strength here, once we summarize, strength is gone. And the strength is our response variable, is our predicted variable. We want to keep it. So that's why I'm going to keep that here on the group by level. All right, so next thing, because we want to summarize, we're going to use a function summarize. And now I want to show you a little trick that I don't think we've seen a lot of times. So imagine that we have, I think we have 7 weather columns. So let's think about it. For one side year, for each month, I want to get the summary of that weather variable. So let's say I want the mean Tmax for January, and I want that to be a column. And then the same for February, and the same for March. And then doing that for all the weather, all the combinations of weather by month. That's basically what we're going to do here. And each one of them is going to become a column. Because we're going to be applying a summarizing function to different columns, we're going to use a function called across. So it's gonna, this is not something you've seen yet, but it's another way of you applying the same function for multiple columns and getting the results out in a standardized format. Perhaps if we just code along and run it, I think it's going to be easier for you to see what I mean once it's done, rather than me trying to explain before we do it. So let's call the function across. It has an argument for dot cols, which is where we specify which columns we want to apply a given function across. So the columns we want to apply is going to be, so let's use the C function here and give all the names individually. So we want to give here day L.s, comma, srad.wm2, comma, tmax.c, comma, tmean.c, comma, nvp.pa. So let me just do this like that. Also, we have the complicating effect that we want to, for these columns that we just typed, we want the mean. But for precip, we actually want to get the sum. So we're going to have to specify that in two different steps. One for the variables we want the mean of, the other for the variables we want the sum of. All right, so after you close here on your C function, so that parenthesis right there, give it a comma. The next argument that we're changing here is .fns for functions, which just give it the name mean. You don't want to give the actual function. So if you click on mean, it's going to give you the parentheses. You don't need that. You just need the word mean. And now we need to specify what's the format we want at the end of this. So we're going to say here on the argument .names, the format we want is going to be within quotation marks. We want the new column names to be called mean, underscore, and then the variable name. The way we're going to do that is you give the open and close curly brackets and say .col right here, like that. So let's go ahead and I think this is going to work if we run at this point. We have not finished this chunk, but let's just try to run it. And then let's print it. So you see what happened. So notice that we went from those almost 300,000 rows to about 8,376. So we have year, site, month abbreviated, and strength. But then if you go to the right, now you have a mean, day length. See here. I think we're missing. Did I forget something? Oh no, I think mean abbreviated. Yeah, okay. The month is not in the name yet. The month is a column at this point, but that's going to change. But for now, so we have the mean day length, mean solar radiation, mean Tmax. Notice that this format that we gave here, mean underscore .col, is just populating with those columns that we specified on top. Now we got all the columns that we needed for the mean, but we also need to get, for precipitation, we need to get the sum, the cumulative effect of that. So right after these names here, if you have some lingering parentheses down here, you can just bring them up because one of them is going to close that across. So this one is closing the across, and the last one is closing the summarize. So in between them, you can break line to help you. So we leave the one that's closing across here, so it's easier for you to see. Give it a comma. We're going to specify now how we want to summarize precipitation or any variable that we would like a different function other than mean. We're going to use again the function across at this level. The .cols is going to be equal to just one value, which is prcp.mm for precipitation in millimeters. Now here the .fns argument, which is for the function, we're going to call sum. And then the names, we're going to say, in quotation marks, sum underscore curly brackets .col curly brackets. Okay, so there was a lot of, parentheses and commas here, so make sure that you got all of them right. Now, if you run this, and you print FE month sum and go all the way to the right, now we also have a sum precip in millimeters as the last column. Notice again, we have to give two across functions within the summarize because the first one is applying the mean function and the second one is applying the sum function to the summary. And now lastly, I don't know if you noticed this as well, but every time you every time you apply a group by, that data frame comes out with that group structure. Sometimes that's okay. Sometimes that causes some trouble down the road where you want to do something not by groups and the group structure is still there. So just to make sure that now we group by, we apply what we want to those groups. Now let's just ungroup. So do a pipe and let's ungroup to make sure that our data frame is not a group data frame at the end. So if you run that and you print it, notice now it does not say groups here on top. It just gives you everything we have there. Okay, so we have now 8,376 rows and 10 columns. Any guesses why we have 8,376 rows?
Light years multiplied by number of months.
Yes, right. So we have 650 or 698 side years times 12 months, 8,376. That's exactly it. Thanks, Omar. So, yeah, so now we have the summary by month, but we still have month as a column, and we're gonna have to change that in a second. But before we do it, let's just check here. Basically to double check that the value that we're getting for Altus, Oklahoma in 1980 in January is what we were expecting. Just to make sure that whatever happened on this level of the data set is actually what we were expecting. So my comparison here is I want to compare, let's see what variable we're using here. We're using Tmax and Precip. So the Tmax value for the first row, which is Altus, Oklahoma 1980, I want to see if this value here of Tmax and the cumulative Precip actually match if I were to do more in a more manual way, which is what the following chunk is doing. It's taking FE month, which has all the data, only filtering the year 1980 and site Altus, Oklahoma, and the month January. So if I just extract this for you, this is what we get. So this is all the 31 days in January 1980 for Altus, Oklahoma, and then summarizing to get the mean maximum temperature and the sum of the precipitation. So if we run this, these are the numbers we get. If we compare that with what we did above with everything, so 10.17 and 61, 10.17 and 61. So the first row here was Altus, Oklahoma 1980, right? So just double checking to make sure that it did what we intended. Okay, so now what if we wanted to actually have month as part of the column name instead? Instead of having month as a column, so right now, let me show you here again, month is a column. But I want this column to not be here. I want to have mean day length in January as a column, mean day length in February as a column, and so on. So all combinations of the summarized weather variables by month, I want them to be a column instead of being like this, because that would be the format you would feed into a machine learning model. So that's what we're going to do on the next chunk here. Let's start typing and give it the assignment symbol. We're going to start with the object that we created above, which was FE month sum. So I'm going to do a little trick here that I don't think we've done before. So it's a new trick on your toolbox. So the first thing we have to do here, let me print FE month sum. So I want to first pivot longer and have a column that has the variable names and a column that has the weather values. And now that I have a column with the weather variable names, I will join that with the month information. And then I'm going to pivot wider again, this new column, which has variable and month, going back again to the column names. You know what? I think that maybe, because we're going to 11:30 today, we have 6 minutes, and I think this chunk is an important one. I don't want to rush. So maybe this is going to be a good stopping point for us. So let's just stop here and do this on the next class. And then we'll finish this exercise on next class, and then we're going to start on next exercise, which is going to be an exercise on multicollinearity, how that can be an issue, how we can address that. So we're going to talk about that. Yeah, I think that's it. Okay, so Aminder, did you have a chance of opening the issue? All right, thank you. So make sure you claim your attendance. Go on GitHub and claim your attendance. Make sure you save your script. And then we're gonna continue and finish this exercise on Tuesday. I guess any questions about anything? Yes.
When should we expect the main term?
Yeah, so next Monday is my plan. Yeah.
Sorry, I must have.
Yeah. All right. Any other questions or perhaps code issues or anything else?
What if we
Dr.
have?
Vestas.
Oh, sorry. Go ahead.
Go ahead, Shakir.
So I was finishing the repeated measures exercise. So
Mhm.
it's kind of funny. The first time that I was running the intervals, I was getting the same results as yours.
Mhm.
But for some reason, I had to close the project. And then I reran all chunks. Interestingly, some of the chunks, they were giving no outputs that I was getting output before.
Mhm.
So I don't know what's going on.
Yeah, so I remember this happened last year as well. And I'm trying to remember if we identified a cause. I don't know if we identified a cause necessarily. It could be related to, I think there may be some part of the function that is doing, it has some randomness component to it. Like it has some part of the function that is choosing a starting point perhaps. That randomness component gives slightly different results. Yeah, I think that's what was going on.
Okay, thank you.
Selvin, you had a question?
Yeah, in the code above where we were summarizing the data, what if we have NA values there? Is there any way to specify like missing observations?
Yeah, so if we have NA values, I think that if you're just specifying like I am here, I think you would get an NA back. So what I believe there's probably, let me see here. So there's a cross function, probably has some other arguments. Let me see. Let me do a quick help on a cross. Because it's gotta have a way of you to say NA remove equals true, which is what we do when we're applying the mean function and we have NAs. Let me see if I can search here. Oops. No. Let's see. Trying to see if I find an example that they give here with that. Maybe what I would try, because sometimes these functions, so if you see a cross is applying the functions here, right? The function mean. Sometimes if you just give the argument of that mean function, which is na.rm equals true, sometimes that works. Let me try here. That doesn't hurt. Try. Let me stop recording as well. We can continue troubleshooting that.